So now I'm going to discuss integrating a function of several variables. So for example, suppose that f is a function from R2 to R. For example, maybe f of xy is equal to x times y squared, just for one example. What would it mean? What does it mean to integrate f over some region in the plane, some region in R2, like this? Let's call this region R. Here's the x-axis, here's the y-axis, and f is a function. You give it a point in the plane and it gives you a number back. If you think of this as being a physical object, then maybe f tells you the density of the object at each point in space, for example. So what do we mean by this expression, the integral over r of f of x, y, dA? What does this expression mean? So here's what it means. What it means is we're going to take the region that we're integrating over and we're going to chop it up into tiny pieces, and we're going to compute the contribution of each piece, and then we're going to add up all those individual contributions. That's what we always do in integration. Chop up the region we're integrating over into tiny pieces, compute the contribution of each piece, add up all those individual contributions. So here we are chopping up R into tiny pieces. The pieces don't have to be rectangles. Often they might be rectangles, but they don't have to be. So we're chopping up R. Okay, now we have to compute the contribution of each piece. So let's look at this specific piece here. How do we compute the contribution of this one piece, this one individual piece right here? Well, here's what we do. We select a point arbitrarily inside this little region. And that point, let's call that point xi star, yi star. And the I is a subscript. This is the ith piece of R. We've chopped R into maybe 100 tiny pieces. This is the ith piece of R. And now we're going to compute f of xi star, yi star. In other words, we evaluate f at this point, and then we multiply by the area of this little region. So we multiply by the area of this little region, and I'm calling that area delta AI. So this number here is the contribution of this one piece, the ith piece of R. And then we're going to add up all the contributions from all the individual pieces. And this sum that we get here, this is approximately the integral over R of f of x, y, dA. Now, why do I say only approximately? Well, if we wanted a better approximation, we could just go through this procedure again, but next time chop up R into even tinier pieces, super tiny pieces. And when we do that, we're going to get an even better approximation to the integral. So this integral is a limit of sums like this as the size of the pieces approaches 0. This sum is called a Riemann sum. And this integral is a limit of Riemann sums. So if you want the approximation to be extremely good, then chop up R into extremely tiny pieces, and then you'll get an extremely good approximation.